Okay, so we have seen how is it possible to evaluate the specific heat of a solid using or different approximations that are the low temperature one and the high temperature one, or using the Debye model that through some approximation tries to find a closed expression for the CV dependence on temperature. And the final result is that if we plot T on the horizontal axis and the specific heat on the vertical one, then as predicted by the classical models, the high temperature value approximates the long MPT expected value for the specific heat, and at low temperature, we have the just concerning the phonon contribution, we have the T to the power of 3 dependence on temperature. And the only thing that I would like to recall now is the fact that this, let's say, regarding the phonon energies, the parameter that somehow describes the intensity or the strength of those energies is the Debye temperature. And the Debye temperature was defined by, let's say, the Debye approximation that was that the maximum energy of a phonon whose wave vector is kd, and kd is defined through the constraint concerning the volume of the Debye sphere, that this energy divided by the Boltzmann constant gives us an estimate of the energy of the maximum phonon state that we may have in the system. So this parameter here is a sort of temperature equivalent of the maximum energy of a phonon. And in this case, this temperature separates the two regimes. So the high temperature one and the low temperature one are separated by this temperature here. So due to the fact that, let's say, if we make just have a look at the tables where the Debye temperature are presented, and if we look at the actual CV versus temperature dependence for the common solids, what we find is that theta D is the order of hundreds of Kelvin. So it ranges from, let's say, less than 200 up to 400 or 500 Kelvin for general solids. It may have also higher values, but the typical value is again of the order of some hundreds of Kelvin. So in this picture, we have the separation between the, let's say, classical behavior of the phonon system and the quantum mechanical behavior of the phonon system can be both accessed just by switching the temperature in a range that is, let's say, comparable with the temperatures that we usually may access during an experiment. So low temperature, that means below room temperature, and high temperature means a temperature of the order of some hundreds of Kelvin. So all the temperature can be accessed. So at this point, if we concentrate on the phonon system, we may access both the classical and the quantum mechanical behavior of that system. The equivalent of the Debye temperature when we studied the electronic system was, so this is for phonons. The equivalent for electrons is the Fermi temperature. So, and the Fermi temperature was obtained by using a similar method. So we compared the maximum energy, the Fermi energy for one electron divided by Kb. So this temperature is again an equivalent of the strength of the Fermi energy just in the scale of the temperatures. And in this case, we have that the let's say, typical value of the Fermi temperature is in the range of 10 to the 4 Kelvin. So this is larger and larger with respect to the Debye temperature, and is larger and larger with respect to the typical temperature that we may access in the lab, or in the lab. So the point is that while for phonons, we may switch from the quantum mechanical to the classical behavior just by changing the temperature in a, let's say, in a range that may be accessed in the lab. In the case of the electronic system, we may not access the, let's say, classical behavior of the electrons, because when the electrons may behave in the classical way, then the solid has melted, the solid is gone to the vapor phase, because at this temperature you have no more solid state. So in this case, you may not access the same opportunity to switch from the classical to the quantum mechanical behavior. And the fact that for phonons is possible to access both regimes is due to the fact that if we plot the usual diagram where we have here h bar omega of k, so we plot the three different branches that we have, for instance, for the acoustic phonons. Then we have that due to the energy of the excitation, this energy here is of the order of tens of milli eV. And as kBt, when we consider 300 Kelvin is 25 milli eV, then this temperature and this temperature, if we consider the temperature expressed in milli eV, are comparable with each other. So due to that, as you change the temperature, you may switch from this behavior down to this behavior just by, again, changing the value of the temperature along the expressed in energy along the vertical axis of this scale. So in this case, we may go through the phonon spectrum just by changing the temperature, while in this case, if we just consider the temperature, then we are always far, far away from the Fermi energy, because the Fermi energy is of the order of, let's say, 3, 5 EVs, while the room temperature is 25 millieVs. So in this case, there's no direct comparison between this value and that value, but luckily this value is comparable to those values here, so we have this kind of behavior. So if the same picture for electrons was valid also for phonons, we would be just able to access the t to the power of 3 dependence. But thanks to this similarity, then we appreciate the full dependence. And concerning the comparison between electrons and phonons, so apart from the different scale of energy, we also had the opportunity to access also the specific heat contribution coming from the electrons. And in that case, we found that the dependence of the electronic specific heat on temperature is linear. So what we found was, say, if we know that the specific heat contribution coming from the electrons is linear as a function of temperature, we may expect that when we have a look at the CV dependence on temperature at low temperature, then we have the e to the power of 3 that is due to phonons. We have a linear contribution. We have a linear contribution due to the electrons. So we may expect that at some temperature there will be a crossing from the between the electronic dependence and the phonon one. So what I would like to do now is just to give an estimate of this crossing temperature. Why should we do that calculation? That calculation is useful just to have an idea of what is the range of temperatures where you may expect to find only the electronic contribution, that is more or less this range here. So here the electronic contribution is the dominating one, but up to say for temperatures higher than that, then you have that the phonon contribution is the leading one. So that temperature separates, let's say, the regime, the temperature regime where you may expect to observe a phonon contribution from the temperature range where you may expect to find the typical phonon contribution. So to do that, we may, since we are just discussing what happens at low temperature, we may just refer to the, let's say, phonon dependence that was obtained at the end of the calculation using the Debye model. And in that case, we found that the phonon contribution at low temperature concerning the specific heat is equal to 234 T divided by the Debye temperature to the power of 3 times the ionic density times Kb. Since in a while I will have to use also the electronic density, I just write an E label here to say that when we consider the contribution of the specific heat coming from the phonons that are related to the ionic motion, then here we need to set the ionic density. When we consider the electron contribution, in this case I write low T, but in this case the distinction between low T and high T, where high T and low T are the high temperature and low temperature regimes for the phonon, has no meaning, because for what concerns the electrons, we are always at low temperature for the electrons due to the value of the Fermi energy. And in this case, the specific heat is pi squared divided by 2, temperature divided by the Fermi temperature. In this case, we have a density, but this is the electronic density, Kb. Just to simplify the just to simplify the comparison, I assume that Z is equal to 1. So just 1 electron per ion is shared with the system for what concerns the electronic, to build up the electronic system. So due to that, the Ni is equal to Ne. So the electronic density and the ionic density are the same. So in this case, we have 234 T divided by the Debye temperature to the power of 3. Then we have the, I just write N at this point because the two densities are equal. So I just write here N, then we have Kb, and this is equal to pi squared divided by 2, T divided by Tf, and Kb. So if we simplify N and Kb, then we have here this temperature can be simplified. So here I just write T to the power of 2 and Debye temperature to the power of 3. So at this point, we may write that T to the power of 2 is pi squared divided by 2. Then we have 1 divided by Tf. Then we have the Debye temperature to the power of 3. Everything is divided by 234. If we use, just to insert here some values, the parameters for calcium, in this case, the Debye temperature is 230 Kelvin, and the Fermi temperature is equal to 5.4 times 10 to the 4 Kelvin. So if we set those parameters here, what we have is that T is equal to about 2 Kelvin. So in this approximation, the crossing between the phonon dependence and the electronic one takes place at about 2 Kelvin. So in this case, to appreciate the switching from electronic to phonon behavior, you have to go down to a really low temperature. And in particular, you expect to find this, let's say, change of dependence of the specific heat on temperature only for metals, because the electronic contribution that comes from, let's say, nearly free electrons, or in the nearly free electron approximation, can be observed when you have that actually the electronic density close to the Fermi energy changes depending on the temperature. So that happens if the electronic band is not completely filled. If that is filled, then you have no change of occupancy because the band is always filled. So in this picture, for metals, you may expect to observe this T to the power of 3 here, and this dependence proportional to T at this temperature. So in this picture, again, you may observe the specific the contribution coming from the electrons, but that contribution is really at low temperature. Going on with the let's say with the comparison between electronic features regarding the specific heat or the typical energies of the electrons and the corresponding phononic features, one thing that I let's say told you when we started the discussion of the properties of the ionic crystal, in case the ionic crystal is able to oscillate with respect to the equilibrium position, was that we may use what was called the adiabatic approximation. The adiabatic approximation meant that for any arbitrary configuration of the ionic lattice during the oscillation, the electrons can be considered to be always in equilibrium with that configuration. And this hypothesis was justified by the fact that I told you that the average velocity of the electrons was higher and higher with respect to the typical velocity of the propagation of the ionic oscillations through the lattice. So at that point, that assumption could be considered to be fine. As I never demonstrated that, I just wanted to take the occasion to compare to make a comparison between the typical electronic velocity and the typical phonon velocity. To make this comparison, so to compare the phonon and electron velocities, then we may start the discussion comparing their energies. So if we, just to make it a simple, to use a simple expression for the electronic energy, if we consider the, let's say, free electron picture, then in that case, the maximum energy for an electron, so in the free electron approximation, this is the maximum energy that may correspond to 1 electron in the system. On the other side, if we consider the phonon system and we use the Debye approach, in the Debye approach, we know that the maximum energy for a phonon in the system is h bar omega d. So this is the Debye approximation. So using the free electron approximation for what concerns the electrons and using the Debye approximation for what concerns the phonons, we may say that h bar squared kf squared divided by twice the electronic mass is larger and larger with respect to h bar omega d. And due to the Debye approximation, h bar omega d is equal to h bar c, and c is the average speed of the lattice oscillations in the Debye approximation times kT. So we have this comparison between typical Fermi energy, typical energy of 1 electron at the Fermi surface, and typical energy of the maximum phonon that we may have maximum lattice oscillate of the maximum energy of a lattice oscillation that we may have in the system. Kf represents the Fermi wave vector. Kd represents the Debye wave vector. So they both correspond to the, let's say, to the radius of a sphere that includes, in this case, of all the electrons that we have in the system, in this case, all the possible wave vectors that correspond to phonons that we may have in the system. In principle, Kf is not equal to Kd. So it's not said that those two values are equal with each other, but what they share is the order of magnitude, because they are both comparable with the size of the first Brillouin zone. So just as a rough approximation, we may say that Kf is similar to Kd in the sense that, again, they have not the same value, but they share the same order of magnitude. So more or less their range of values are similar. So due to that, in this expression, we may simplify h bar Kd with h bar Kef. So using this approximation, and so making the simplification between one of the Kfs that we have here and this Kd, we have that this is equal to h bar Kf divided by twice the electronic mass is larger and larger with respect to c, where c is the speed of sound in the system. In the free electron approximation, h bar Kf is the electronic momentum. Momentum divided by the mass is the speed of the electron. So this means that the, let's say, the Fermi velocity divided by 2 is larger and larger with respect to c. So what we have found, what we have obtained here is that, again, using these two approximations just to have a reference value for what concerns the expression of the electronic energy and the phonon energy, we have that the comparison between the speed of the electrons and the speed of the phonons is in favor of the speed of the electrons. So this is one occasion where we have the opportunity to compare these two values and to find that, as it was said, the velocity of the electrons is larger with respect to the velocity of the phonons. There will be another opportunity, I think, next week to make a comparison between these two quantities and to again confirm the fact that the actual speed for the electrons is larger than the one corresponding to phonons. And yeah, I would like just to have some a couple of things concerning the just one last thing concerning the topic of the specific heat before going on with the next section. When Debye, what I'm going to do now is just a comparison between what we found using the Debye approximation. So in the Debye approximation, we have that the total energy, I think it was the total energy due to just the ionic oscillations could be written as 3 times, because the sum over S gives 3 times the same value. Then we have the d3k, then we have 2 pi to the power of 3. If we divide by the volume, then the volume that comes from the volume element disappears. Then we have h bar omega of k, and then we have the exponential of h bar omega of k divided by kBt minus 1. So this was the expression with this relationship when we made then the substitution of omega k. We replaced omega of k with just c times k, and this was one of the Debye approximations. So this was the this was the starting point of the Debye calculation, and the Debye calculation was performed based on the hypothesis that the frequency of the lattice oscillations was not constant, but dependent on had this dependence on the wave vector of the oscillation itself. So depending on the wavelength of the oscillation, that we have a frequency, and we observed that that value of that frequency may go to 0 as the wavelength of the oscillation increases. In this case, I'm just considering acoustic phonons, because for optical phonons, this approximation is not valid. So at around 1912, 1913, Debye discussed this approximation and obtained the result that I show you. But this was not the first trial for what concerns the evaluation of the specific heat, or in general, for the evaluation of the energy of the oscillations of the ionic lattice. Because Einstein, about 6 years before, used a different approximation for what concerns the evaluation of the specific heat. So this is the Debye approach. In the case of the Einstein approximation, Einstein assumed that within the lattice you have the opportunity to observe oscillations of the ions. But in that case, he assumed that the dependence of omega of k was just a constant value. So he assumed that the frequency of oscillation had no dependence on the wave vector. Now, knowing what is the result of the full calculation, applying the quantum mechanical approach to the behavior of the ionic lattice, then we know that this situation corresponds to the optical phonons. But at that time, the assumption was that, again, no dispersion for what concerns the omega versus wave vector dependence, just a constant value was observed for all the oscillations. In that case, if you make this integral using this assumption, then what you have is that at the end, let's say, the total energy due just to the oscillation, if we write the initial summation, so the first expression that they gave you for what concerns the total energy was the equal to the sum over k and s of h bar. In this case, I have just omega e, so the energy is only omega e, and then I divide by the Bose-Einstein distribution value. So I have just this number here. As here, nothing depends on the indexes of summation. So omega e does not depend on k or on s. This is equal to 3 times n h bar omega e divided by the exponential of h bar omega e divided by kBt minus 1. So at this point, if we use this expression to evaluate the specific heat, then the specific heat is equal to 3n divided by the volume. Then we have h bar omega e, and then we have the derivative of this function with respect to temperature. So what we have is the exponential of h bar omega e divided by kBt minus 1 squared. Then we have the exponential then we have the derivative of what is within the exponential. So we have h bar omega e divided by kb and 1 divided by t squared. Then I should include here one minus sign here because I have the derivative of a composite function where I have 1 divided by the function that I want to make the derivative of, and then I am again making the derivative of 1 over t. So in that case, I have another -1 here. So -1 just gives you a +1. And if you include, let's say, if you want to write this as 3n divided by volume, then we have this exponential factor. So if you don't mind, I just write like this. Then here we may write this as h bar omega e, because we have one h bar omega e here and another h bar omega e here, then divided by kbt squared. But since I have just one kb here, I include another kb here. So at this point, everything is fine. And if we look at this expression, then when t goes to 0, what we have is that in this, when t goes to 0, the term that we have within the exponential is very large, because h bar omega e is a constant and kbt goes to 0. So if we look at the denominator, we have the exponential of something that is very large, -1. So we may neglect the -1 with respect to the exponential term. Then we have this exponential factor divided by the same exponential factor to the power of 2. So we have 3n kb divided by the volume. Then we have the exponential of minus h bar omega e divided by kbt times h bar omega e divided by kbt squared. So here we have something that as temperature goes to 0, goes to 0. And here we have something that shows in principle a divergency when t goes to 0. But the exponential term is stronger. Sorry, at this point, if we consider the limit, the leading term is the exponential one. So this expression actually goes to 0. But when this expression goes to 0, you have an exponential term that is dominating. So this means that the approach to the CV equal to 0 value is faster and faster with respect to the typical approach that was observed in the experiment. So in the experiment, you observe a t to the power of 3 dependence. In this case, we have an expected dependence that is faster as the as the temperature decreases. So due to that, again, when this model was applied, it gave a general expression that was, let's say, comparable with the expression that was expected for the specific heat, if both at low temperature and at high temperature. But the main drawback was that the decrease to 0 was too fast with respect to the measured one. So when the Debye model was proposed, and the Debye model considered the actual dispersion of the frequency with respect to the wave vector, that gave a better approximation for what concerns the phonon contribution, because when the temperature goes to 0, you have that mainly acoustic phonons contribute to the system. So the acoustic phonons are exactly the phonons that are included by the Debye approximation. So in this case, the agreement with the experiment was better for what concerns the low temperature dependence. Anyway, since the Einstein model, that starting from the approximation that was not fine for the acoustic phonons, but is actually fine for the optical ones, is useful to, let's say, introduce, in case you have a solid where you have also the contribution coming from optical phonons, is useful to, let's say, introduce or to include their contribution to the expression of the total energy of the system. And due to the fact here we see a consequence of the fact that the energy of the optical phonons is always larger than the energy of the corresponding acoustic phonons. The consequence of that is that at low temperature, the decrease to zero of the, let's say, now optical phonons to the specific heat goes to zero faster and faster with respect to the contribution that comes from the acoustic phonons. And this is just due to the fact that the, let's say, the typical energy of the acoustic phonons is smaller with respect to the typical energy of the optical phonons. So a consequence of that is again the fact that the probability to have optical phonons excited at low temperature is smaller and smaller with respect to the probability to have acoustic phonons excited at low temperature. And due to that, you have this different approach to zero coming from the, let's say, Einstein model that can be now applied to optical phonon with respect to what is observed for acoustic phonons that are discussed by the again the Adiabatic approximation. Okay, so after this comment, I have just one last point that I would like to discuss with you, and is just let's say a comparison between a result that I think you have already observed during the bachelor degree. And if you consider again the total energy of the system per unit volume, when you consider the Debye approximation. So in this case, if we divide by the volume, what we have is a factor of 3. Then if I switch to spherical coordinates, then here I have the 8 pi to the power of 3. Then here I have h bar ck and the exponential of h bar ck divided by kbt minus 1. Then I have the integral over the angular variable, but in this case, nothing depends on the angular variable. So I have a 4 pi here. I may simplify this 4 pi with this 8 pi to the power of 3. So I have a 2 pi to the power of 2 at the denominator. And okay, so in this case, if I use this expression and I go back to the omega, I reinsert omega here. In this case, I may replace this ck with omega, this ck with omega. Then, since ck is equal to omega, then I may replace this k squared with omega squared divided by c squared. So if I make this change of, so if I just reintroduce omega into this expression, then I have that the energy per unit volume is equal, and I also make the change of variables here. So I switch the integration over dk to an integration over omega. So I have the 2 pi to the power of 2 at the denominator. In place of dk, I have d omega. I have one C factor due to the change of variables regarding decay, so I have 1 over C due to that. Then I have omega squared divided by C squared coming from the this K squared factor. Then I have omega, another H bar omega here, and then I have the exponential here below. And minus 1. At this point, I may also include another change of variables, in the sense that I may write omega as 2 pi times the frequency. So in this case, if I also make that change of variables, I have 3 times divided 2 pi to the power of 2. Then before doing that, I just collect everything here. So I have d omega, then I have omega to the power of 3, h bar omega to the power of 3 divided speed of sound to the power of 3, and then I have 1 divided by the exponential of h bar omega divided by kBt minus 1. If I now replace omega by 2 pi times a frequency, what is the idea behind this substitution? The idea is that this integral is the integral that tries to, I forgot to write here that the initial integral was from 0 up to kd. When I switch to frequency, the upper limit is omega d. So in this case, the upper limit is omega d. In this case, what you try to do is to find the total energy of a system, and the system is at the end a box, and in that box you have particles. In this case, the particles represents the excitation of the displacement field that describes the position of the ions within the solid. So you are trying to evaluate the total energy of a system of oscillators that are found within this cavity, and the cavity is the solid state, is the sample you are investigating. You made a similar calculation concerning the total energy of the normal modes of oscillation of other oscillations within a box, within a cavity, and that calculation was done in the case of the black body radiation. So in that case, the aim of the discussion was not to describe the motion of actual atoms or electrons, but that was about the, let's say, the discussion of the energies of electromagnetic waves of the phonons within the black body cavity. So I would just like to rewrite this integral concerning phonons using the same variables that were used for photons. In that case, the variable of integration was the frequency of the photons. So that's why I just would like to rewrite omega as a function of the frequency to find an expression. So to try to write down an expression that has the same variables of the black body case. And another thing that I should modify to see whether this expression may be or may be not similar to the one that was observed in the case of the black body radiation concerns this factor here. This factor 3 comes from the fact that if you fix the wave vector, you have 3 possible polarizations for the ionic oscillation. One polarization is longitudinal, and then you have 2 transverse polarizations. For what concerns the electromagnetic waves, you have not 3 possible polarizations, you have just 2 possible polarizations for what concerns the photons. So in this case, I multiply everything by 2 divided by 3. So I divide by 3 because I just want the contribution of just one of the possible polarizations, and I multiply by 2 because in the case of the photons, you have 2 possible polarization states, not 3 as you have for phonons. So in this case, you have a 2-factor divided, so you have 2 divided by 2 pi to the power of 2. In the case, the integral is from 0 up to the d by the equivalent of omega d expressed in terms of the frequency. D omega is transformed into d frequency times 2 pi. Then we have h bar, then speed of sound to the power of 3, then omega is equal to the frequency to the power of 3 times 2 pi to the power of 3, and then we have the exponential of h bar omega with this expression for omega is equal to h times frequency divided by kBt minus 1. So at this point, we have that this this 2 pi times h bar gives us just the Planck constant. Then we have this, may simplify these two and these two. Here we have 8 pi to the power of 3, then pi to the power of 2. So we have just an 8 pi here. Then we have the speed of sound to the power of 3, integral from 0 up to the bifrequency, and then we have this integral, so h omega to the power of 3 divided by the exponential of h frequency times divided by kBt minus 1. And this is exactly the same expression that was found in the case of the black body radiation. And actually, if you remember, I will later comment on that. So this is exactly the same result. So the total energy of the electronic system, the total energy of the phonon system, that are the possible oscillations that you have in the cavity that is represented by the solid you consider, is expressed by an integral whose and the term that you have within the integral and also the coefficient is exactly equal to the one that was observed, the one evaluated the total energy of the photon system, of the photons that you have that you had in the not photons actually, but of the electromagnetic waves that you have within the cavity. In that case, the integral here was not from 0 up to the bifrequency, but was from 0 to infinity. So all possible over all the possible frequencies that one could find within the electromagnetic waves spectrum. And in that case, if you remember, the main problem that was solved thanks to the Planck contribution was the so-called ultraviolet catastrophe that was due to the fact that the, let's say, without this term here, you had a divergence of the total energy of the system in the high frequency range. So in the case of the black body radiation, the problem was when h times the frequency was larger and larger with respect to kBt. So when you increase the frequency, if you use the classical approach, and the classical approach means that the average energy per normal mode of oscillation was not given by the Planck term, but was just given by kBt. So in that case, the divergence was observed in this regime. If we consider the phonon system, In the phonon case, regarding the evaluation of the specific heat, then the problem was at low temperature, because at low temperature, the classical result was not fine. Now, what happens at low temperature? At low temperature, if this symbol here represents the frequency of a phonon, then at low temperature, in general, you have that the average energy of one phonon is larger and larger with respect to the typical thermal energy. So while at high temperature, we have exactly the opposite situation, then at low temperature, this situation appears. That is exactly the same situation where the black body radiation in the classical approach failed to describe the actual results of the experiment. So the deviation, let's say, from the classical picture is observed in both situations for the same condition. So when the, let's say, typical energy of the oscillation that you try to evaluate, sorry, that you consider in the system, in that case, we had, in the black body case, you have electromagnetic waves. In this case, you have just phonons. So both the problems arise exactly in the same condition. And so I just wanted to recall this to stress the similarity between this problem that we have here and the black body problem that was found when discussing the properties of the black body radiation. And just as a last comment, if you remember the evaluation of the specific heat in the low temperature approximation, then in the case of the phonons, so low temperature phonons, we found that the total energy of the system was proportional to T to the power of 4. Then we made a derivative and we had the T to the power of 3 dependence of the specific heat. And if you remember the black body case, also in that case, the total energy depends on T to the power of 4. You have the Stefan Boltzmann law that tells you what is the relationship between the total energy that is stored in the cavity and the temperature. And also in that case, you have a T to the power of 4 relationship that relates the two quantities. Okay, so again, this was just to make this comparison between that situation and this situation. And yeah, I'm sorry, I'm going a bit, say now is 10 past 10 minutes, or we have 10 minutes past 10. So I spent maybe too much time in this first hour. And I now stop the registration so we may have a break. And